In this experiment, we investigate the chemical properties of group 2 element through three main stages: the flame test, the acid-base character test, and solubility test with different reagents. Each step was designed to observe periodic trends and relate experimental observation to atomic structure and bonding. The first one, flame test. First, the experiment began with the flame test to identify characteristic colors of group 2 metal ions. When magnesium chloride was introduced into the flame, no distinct color was observed. This happened because magnesium emits radiation mainly in ultraviolet region, which is not visible to the human eye. Next, calcium chloride was tested. The flame changed to an orange-rich color. This color appears because calcium excited electron release energy at wavelength within the visible spectrum when returning to their ground state. When strontium chloride was placed in the flame, a crimson or red-pink color was observed. Strontium emits light at a longer wavelength than calcium, resulting in a deeper red color. Finally, barium chloride produced a green flame. This green color is characteristic of barium and is commonly used in fireworks to create green effect. Overall, this flame color occurs due to electron excitation. Heat energy promotes valence electron to higher energy level, and when they fall back to lower level, they emit light of specific wavelength unique to metal ion. Experiment 2. Acid-base character test. After the flame test, the experiment continued with testing the acid-base character of group 2 oxides and hydroxides using pH measurement. Magnesium oxide produced a solution with a pH of about 8. This indicates that magnesium oxide is weakly basic and only slightly soluble in water. The small size of the Mg2+ ion gave magnesium oxide partial covalent character, limiting the release of hydroxide ion. Calcium hydroxide saw a higher pH of around 11. This means it is moderately basic and more soluble than magnesium oxide. The large calcium ion reduced lattice energy, allowing more OH- ions to dissolve into the solution. Barium hydroxide gave the highest value pH, approximately 13. This confirms that it is strongly basic and highly soluble. The large Ba2+ ions forms highly ion bonds, and the compound associates readily in water, releasing a large concentration of hydroxide ions. This observation shows that basicity increased down group 2 due to decreasing lattice energy, increasing ionic character, and higher solubility of the hydroxide. Third experiment, solubility test. Next, solubility tests were carried out using sodium hydroxide, sulfuric acid, and sodium carbonate. The first one with sodium hydroxide. Magnesium ion produces a clear solution because magnesium hydroxide is only slightly soluble at low concentration. Calcium ions forms a cloudy solution due to the formation of a calcium hydroxide precipitate. Strontium ion shows slightly cloudiness, indicating intermediate solubility. Barium ion remain clear because barium hydroxide is highly soluble. This confirms that hydroxide solubility increased down the group. The second with sulfuric acid. Magnesium ions remain clear because magnesium sulfate is highly soluble. Calcium ion forms a cloudy solution as the calcium sulfate is only slightly soluble. Strontium and barium ion produce cloudy solution due to the formation of insoluble sulfates, with barium sulfate being the most insoluble. The opposite trend occurs because hydration energy decreases faster than lattice energy for large cations, making heavier sulfates less soluble. The third one with sodium carbonate. Magnesium ion remain mostly clear under dilute condition. Calcium, strontium, and barium ion produce cloudy solution due to the formation of insoluble carbonate. In conclusion, the experiment clearly demonstrates periodic trend in group 2 element. Flame tests show characteristic emission color, basicity increase down the group, hydroxide solubility increase, and sulfate solubility decrease. This result align well with the theoretical principle involving ionic radius, lattice energy, and hydration of energy, and electron structure.